Okay, let's discuss IR. IR stands for infrared spectroscopy. Infrared spectroscopy. So this is the same infrared that you would have discussed in General Chemistry 1 when we first discussed the electromagnetic radiation. So all heat sources basically emit IR, just to kind of give you a heads up on that. Let's take a look at the EM spectrum that I'm talking about. The electromagnetic spectrum, which basically has perpendicular electrical and magnetic field vectors, it has various different kind of radiations going through that. We have the radio waves, we have the microwaves, we have the IR, of course, we have the visible going from red to violet, ultraviolet, X-rays, and gamma rays. You can perhaps remember this with a mnemonic: rabbits meet in very unique and, let's just spell it differently, expensive gardens. Radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. All right, now there's certain things that I want you to realize and recall from your physics class or Gen Chem 1, whatever is closer. And that is when you're discussing a wave. Essentially, a wave has two components: the frequency, which is measured in hertz. It can also be written as per second, or wavelength, lambda, which is measured in meters, being the SI unit. So for any wave, there is a frequency associated with it. There is a wavelength associated with it. Now, if I give you two waves, just to kind of discuss what is frequency and what is wavelength. So these are my two waves. We are starting at point O. In both of cases, this is wave 1, this is wave 2. Now the distance that it travels in going from this point up to this point, where it has covered one complete crest and one complete trough, so that's basically one cycle from here to here, and we are going to use the word or the letter lambda to signify the distance that the wave has traveled, and that will be your wavelength. So wavelength is the distance that you have traveled. Wavelength is the distance that the wave has traveled when it has completed one complete cycle, one complete crest, one complete trough. Some people will also say that wavelength is in going in between two successive crests or two successive troughs. Let's take a look how that would be. So this is one crest. The next crest is right over here. So you have covered half of the cycle, and then the trough, and then half of the other part of the cycle, which basically is saying one complete crest and one complete trough. So it's another way of saying the same thing. Notice in the second wave, you're going from point here and you're covering essentially a crest and a trough only up to this point. So let's call it B. Let's call this one A. So in this case, your lambda is right over here. Okay, so lambda is the wavelength which is measured in meters because it's a distance. And hopefully you can see that the number of cycles in going through, let's say we had to cover approximately this distance. Okay, in the first wave you have covered only one cycle, whereas in the second case you have covered 1, 2, 3, almost 3.5. So in this case, you can say that the number of cycles, the number of repeating cycles that you're seeing is higher in case of the second wave, or the frequency, which is nothing but number of cycles per second is higher in case of wave 2. So can I say that as lambda increases, frequency decreases? So if lambda is higher, the number of such cycles is going to be lower. One can perhaps say that. And that would mean that lambda and frequency are inversely proportional to each other, or that lambda times frequency should be some kind of a constant. And if the wave is an electromagnetic wave or radiation, then that constant has a value of 3 times 10 to the power of 8 meters per second, which is the velocity of light that you can perhaps recall from general chemistry 1. Okay, so lots of words, basically to give you an idea of what's where. The gamma rays, like we had discussed in Gen Chem 1, those are the high energy because you're going from radio to gamma, and here is where you have the X-rays, here is where you have the ultraviolet, visible, IR, and microwaves. So gamma rays, these are basically, you can consider cosmic rays. They're emitted from radioactive nuclei as well. They're going to cause damage. So these are greatest in energy and highest in frequency. X-rays, just to give you an idea, again, when you fracture your hand and you need to see the doctor, and the doctor says, well, did you get an X-ray? And they send you to get an X-ray, and the technician asks you, are you pregnant? Because they don't want to give you a dose of the high energy radiation, because essentially it's going to damage the fetus. So it will cause biological damage in high doses. So that's also a high energy radiation. Ultraviolet, all of us know that if you lack the melanin content in your skin, then you need to use the sunscreen to prevent a sunburn. So that too is high energy radiation. Visible light, that kind of speaks for itself. We are able to see wherever the frequencies and the wavelengths are in the visible region. So that's what we see. Infrared, that's essentially heat. We began our discussion with that. You might have seen infrared lamps. When babies are born, they are essentially kept for about 2 hours or so to provide that temperature, the same temperature as the body temperature of mom, before they kind of start getting used to the temperature outside. Microwaves, we cook with them, and they're sometimes used in radar as well, so we're familiar with that a little bit. Radio waves, any kind of telecom essentially is going to apply that, and so these are, thank goodness, slightly lower in energy as compared to gamma rays. They're all around us essentially, so these are low frequency and hence low in energy as well. Another time that you saw radio waves was when we discussed NMR. So, long story short, those were the various different kinds of electromagnetic radiations. Any and every radiation will have a frequency component and a wavelength component associated with it, and the number that goes basically gives you an idea whether or which kind of a radiation we are referring to. All right. So just gave you this generic formula that lambda times nu is equal to c, the velocity of light, and that happens to be a constant having a value 3 times 10 to the power of 8 meters per second. Okay, now, when we first discussed quantum mechanics, your teacher would have given you another relationship that energy of the radiation is proportional to the frequency of the radiation. What that means is that higher is the frequency, higher is the energy associated with it. And so when the sign of proportionality is removed, the constant is introduced, which happens to be the Planck's constant in this case. The H is Planck's constant. And when we replace the value of nu, since we know that lambda times nu is equal to c, that would mean that nu is equal to c over lambda. We are dividing both the sides by lambda. And so you're replacing the value of nu, you're incorporating that into E, and your relationship for the energy of radiation starts to look like E is equal to hc over lambda. This is a Planck's constant. C is a constant as well. What does that tell you? That tells you that energy is inversely proportional to lambda, to the wavelength. That means higher is the wavelength, lower is going to be the energy. What does that tell you? So again, writing that panel, rabbits are meeting in visible going from, in my head, I always see this as infrared. So red must be closer to that because infra would be less than that, and this is violet, hence it will be closer to ultraviolet, and x-rays and gamma rays. Okay, so hopefully that tells you that red, which has a higher lambda, higher wavelength, radio waves is the side where you have high lambda, gamma rays is the side where you have high frequency. So if your wavelength is high, that would mean that the energy is going to be low. What does that tell you? That means radio, micro, as well as infrared are low energy radiation. And that's an important point. The reason being, because all of this, I'm not trying to reinvent the wheel and kind of go over what you already know from Gen Chem 1, but we want to now apply the infrared spectroscopy, the irradiation of any organic molecule with IR, and see what happens. So the first thing that I want you to think about is that infrared radiation, it does have some energy associated with it, but it is not an energy which is so high that is going to start breaking bonds. That means this is a non-invasive. It's pretty non-invasive. It's not going to break any bonds. It's not going to change the chemical makeup of your organic molecule. And that's a very important point. That means we can use an IR on an organic molecule, get the data that we want, and still collect the organic molecule in a bottle and use it for whatever we need it to use it for. So for instance, if you isolated and purified and you have like very little sample of maybe only a milligram of an organic compound from a sponge in the Gulf of Mexico, let's say, and you wanted to study, you wanted to see what the structure is like, you wanted to get some information, what you would do is you would take an IR, you would irradiate it with the IR, you would get the pertinent information from the IR, and then you would collect the sample and you will reuse that for, let's say it had some biological activities, so you're going to reuse that for whatever biological needs that you needed it for. So IR, the strongest point or one of the strong points would be that it is a non-invasive technique. That means you don't lose the material that you began with. Okay. So again, emphasizing on the same thing, high frequency means short wavelength and high energy. So nu, which is for frequency, and energy, they kind of go hand in hand. And lambda is inversely proportional to the energy. Now, like I said, IR is the region of low energy, and we are saying that E is equal to Hc over lambda. The energy in the spectrum is measured in what is called as a wave number, which is 1 over lambda. So that's a wave number, centimeter inverse. It is, you can call it inverse of wavelength, and hence it is a parameter which is proportional to the frequency. So it is just associated, when you would read the spectrum, it would be read in centimeter inverse. So you can say that energy is equal to h, which is Planck's constant, c, which is the velocity of light, and this is 1 over lambda. So 1 over lambda is lambda bar. And since these two are constants, you can say that energy is proportional to lambda bar. And energy was also proportional to the frequency. That means these two are proportional to each other. And so realize that this is low energy radiation that we are going to irradiate our sample with. Now, when we start taking IRs, when we start irradiating organic molecules, you will see that the scale kind of goes from 400 centimeter inverse to 4,000 centimeter inverse. Okay, and upon irradiation, the compounds are going to go through some kind of a movement. So several slides are going to follow, but I'm going to use 1 or 2 slides to show you exactly what's happening, so you kind of get a feel for what's going on. Basically, when IR hits an organic molecule, there are 2 different kinds of motions that are produced. Now, before I go into the kinds of motion, I should perhaps tell you that there are 3 different kinds of molecular movements that are possible. Molecular motions that are possible. There is something called as translation, of course, so translational motion. We have the vibrational motion, and we have the rotational motion. Translation motion is that you have a molecule right over here at point A. It actually shifted from point A to B. That means it's changing its x and y and z coordinates, and so you would use the word translation. Of course, in order to do that, you would require a very large amount of energy. Vibrational motion is going to be where the molecule, the organic compound, it just basically vibrates to and fro about an axis, and we'll talk about that. Rotational motion is when you have a molecular axis and the compound kind of rotates about that, and you use the word rotational to signify that. Turns out that the IR basically has the energy to facilitate the vibrational motion. And what that means is that essentially IR would be able to introduce 2 kinds of movements. One, which is called as stretching. The other, which is called as bending. So there is a stretching mode, there is a bending mode. Stretches could be of 2 kinds. You could have a symmetric stretch, or you could have the asymmetric stretch. Bending, likewise, could be in plane or out of plane. Out of plane. So a symmetric stretch would be, you have a, let's just consider maybe A, B, A, generic. I want to keep it as generic as possible. So you have a bond here and a bond here, and if both of them go, consider them like like a rubber band perhaps. So both of them go out and in, and out and in at the same time, by the same extent, you would use the word symmetric stretch. Let's say one of them moves a little, the other extends longer, and then this one comes back, and then this one extends. So this is not symmetric at all. Then we would use the word asymmetric to signify such a kind of movement. If you have like a butterfly type of a movement where, let's say, you have B, you have A, and so the wings are flapping in and out to the same extent, they're synchronized. You would say they are in a plane. And if they are not synchronized, then you would use the word that they are out of plane. So those are the four basic kinds of movements that can be associated with an IR absorption. And hopefully you can see that since these are different kinds of motions, the amount of energy that will be required to go through that movement is going to be different. So on your 400 to 4000 on that scale for the wave number, you're not going to see, for one bond, you're not going to see just one wave number. You can have a bond like, let's say, C double bond O. You can have the bendings, in one wave number, and then the stretches at another spot. So you can have 2 or 3 peaks that correspond to one bond. But there are some characteristic peaks. So when we are studying IR, when we are analyzing the IR, we look for those specific peaks, the presence and absence of which essentially gives you an idea whether a certain bond is present or not. That's the whole point. Now, in your IR, there will be some peaks that will be present in any organic molecule, come what may, because these are associated usually with carbon-carbon bonding or carbon-hydrogen bonding. And so these are going to be present in any organic compound. So usually till about 1300, we don't pay too much attention to what's going on the right hand side of that, but rather what is present on the left hand side of that. That is what we are interested in, because this section is going to be present in all organic molecules. So we call this the fingerprint region. Okay, now in this, I should probably say, in this section, however, there are some peaks, certain regions which are so strong that you would still be able to identify and locate the presence of certain compounds, such as when you have, for example, the CX bond, the C halogen bond, that usually shows up between 600 to 800 centimeter inverse, and it's a really strong peak, and you can't miss that. So when you have something like that, you might be able to, lay more emphasis on that, but the existence of certain bonds is confirmed by the presence of certain peaks. Likewise, the absence of certain bonds also confirms that those particular bonds are not there. So you have to kind of compare, contrast. It also can be used in a relative sense. So for instance, if you're running a reaction, let's say you're converting an alcohol into an alkyl halide, an alcohol will have certain kinds of peaks. The alkyl halide will have certain kinds of peaks, and this should not contain the peaks of the OH. And so those OH peaks must go away. On the other hand, the peaks pertaining the R part, the alkyl part, should still be there. And so you would be able to say that your reaction has gone to fruition or not on the basis of what you see from the IR. Absolutely. All right. In any exam, you would be given essentially this IR table, and even in the assessment, you would use this table. And a copy of that is actually available on Blackboard as well. And so in this particular case, what you're seeing is the various different functional group classes, where they are located and their intensity, whether it's a strong peak, medium peak, or whether it's a weak peak. So hopefully you are able to kind of associate this, that depending on the kind of bond that you have, you will require a certain amount of energy to carry out a vibrational kind of movement. And wherever the wave number is, the energy is absorbed, whatever is that number, that is associated with that group of atoms. What I mean by that is, let's say you have a C double bond O, for instance, which is essentially a ketone, and you're comparing that to C single bond O, which is associated with an ether. So those are two different functionalities, and hopefully you can see that in one case you have a double bond, in the other case you have a single bond. So what do we know about a double bond and a single bond? That's the next question. A double bond is a stronger bond. A single bond is, of course, a weaker bond. So you don't anticipate a greater amount of energy to carry out electronic movement in C single bond O. On the other hand, you do anticipate a greater amount of energy that will be associated with the electronic movement for C double bond O. What that means is that the wave numbers that you're going to see for the C double bond O should be higher, and they are. The C double bond O is going to show up in the 1700 centimeter inverse region, whereas the C single bond O is going to be between 1100 to 1200 centimeter inverse region. So the strength of the bond, of course, dictates the wave number at which you're going to see the compound. And so in that sense, you can say that IR helps you predict functionality. So which functional group you have, you would be able to predict that by looking at your IR spectrum. So you can see here alkanes, they show up 2850 and 2960. The 2850 especially, it's kind of like a side arm, and I'll show you some IRs to indicate exactly what I mean. The side arm is indicative of a free methyl group. So if that is present, then you can say for sure that there is a free methyl group in your structure. Alkenes, the double bond, C double bond C, is at 1640, whereas the vinylic hydrogen, the CH, is 3020. Likewise, alkynes, they are a little bit higher. So if you compare these bonds, essentially this has an sp2 component, this has an sp component, and so it's a stronger, shorter bond, and hence it will require greater amount of energy that will be associated with the electronic movement for that particular bond. All alkyl halides, they are between 600 to 800. Alcohols, the OH is a very broad peak. The CO, on the other hand, is much lower. Those are heavier atoms. It's much lower and shows up around 1200. Aromatic compounds, they show up at 3030 as well. The CC part of it shows up at 1600, and there are overtones that exist between 1600 to 2000. So these are overtones. And there is a file on Blackboard actually which gives you the pattern of the overtones, and based on the pattern you can actually predict whether the peaks are or substitutions are right next to each other, one away, or so let's say you have one Cl here and you have a Br here. So if these are right next to each other, or if they are one away, or if they are completely on two opposite sides, the patterns will be completely different. And you should be able to determine that from the IR. Amines, again, you have a broad peak at 3300 carbonyl compounds. We just talked about that. 1700 is the general range. Carboxylic acids will have an additional OH between 2500 and 3100 or so. Anytime you have a triple bond, irrespective of if it's C triple bond C or C triple bond N, that shows up between 2200 to 2300 in that range. Nitro compounds are at 1540. So I'm showing you three different IRs here. Notice the first one is hexane. So let's just draw that. I always like to number my carbons. I have one hexene then. Then I have one hexine. 3, 4, 5, and 6. Now, when you look at this structure, in the first one you are hopefully seeing, let's analyze that there should be some free methyls and there should be CH2s. That's all I got. And you're not supposed to see this part because that's fingerprint. But I want you to focus in this region. The first sidearm that you see, that is essentially the free methyl. So that is occurring because of the presence of 1 and 6. The 2, 3, 4, and 5, those are CH2s, and so they show up in this region. Notice that essentially peaks are going to overlap on top of each other. That means because you have two free methyl groups here, that does not mean that this sidearm is going to be longer as compared to the sidearm in the next compound. So realize that in case of IR, peaks are going to overlap on top of each other. It's the presence that we are after, but you can't really say that if that particular peak is a strong peak, it means that there's more number of such methyl groups. That is not a true statement. IR is as a technique, it is dependent on concentration. So tomorrow, if you increase the concentration, this peak is going to go longer. It's going to seem stronger. It does have a slight dependence on concentration. So you can't really associate the number of methyl groups in the structure. It's like a relative relationship. Hopefully you can associate that. The second molecule that I have, that's a hexene. So there's a double bond going on. Notice that I have only one free methyl, but I do have it there. And I do see the side arm. These two peaks, those are going to be the CH2s. Notice the peak at 3050, which is for the vinylic hydrogens. And so there are three hydrogens here, 1, 2, and 3, and it's kind of like a medium range peak. It's not that since I have 3 vinylic hydrogens, that peak should become very strong. That's not a true statement. It's again just the presence of, even if you had only one of those, it would show up. The C double bond C, that shows up at around 1600 or so. And likewise, when you look at the triple bond, we have an extremely strong peak at 3300 in this case, the C triple bond C at 2200. The rest of it, of course, fingerprint, we are not interested in that. Again, we are seeing the sidearm, we are seeing the CH2s to signify the rest of the chain. So what is it that we looked for? We looked for the presence of that sidearm to signify that free methyl. We looked for the CH2s. Also, when you're comparing one over the other, if somebody asked you if these three spectra were given and you were told that these are the possibilities, you would be looking at the presence of the double bond, the C double bond C, and the vinylic hydrogen right over here. And you would be looking for the absence of those in spectra A and C. And so again, it's the presence or absence of certain peaks which helps you in identifying which particular compound you have. So you can use IR in an absolute sense, spectra to compound bond by bond, or you can use that in a relative sense in just seeing the starting material and the product. You can use it either way. The slide basically is a general overview, but like I said, the entire table will be provided to you. The fingerprint region is up to about the 1400 mark or so. Past that, all the double bonds, the C double bond O, C double bond N, C double bond C, that's where those show up. Triple bonds follow, and then the single bonds, but realize these contain hydrogen, so there is one light item going on. So the energy that is associated for lighter atoms, that's going to be different than the energy that is associated for two heavy atoms. And so and also it depends on whether these are bending stretches or stretching, so whether these are stretches rather or bends essentially, which dictates the location of the functionalities. But this slide basically gives you sort of like an overview that whenever you have a triple bond, look between the 2000 to 2500. Whenever you have an alcohol or an amine, look past the 2800 for a broad peak. And whenever you have a ketone or an imine or an alkene or an aromatic, look in the 1600 region. Look for the overtones. So it kind of gives you like a generic feel for what's going on. Okay. Usually bond stretching requires a greater amount of energy as compared to bending modes. So if you just compare apples to apples, a CH stretch is going to require greater amount of energy, usually occurs at the 2900 range, than a CC bend, which is in the fingerprint range. Also, the weight, the mass of the atoms that are on that bond, they basically give you an idea of how quickly the vibration will occur. So stronger bonds will require greater amount of energy, whereas weaker bonds will require less amount of energy, for which reason a C triple bond C shows up in the 2100 range, a C double bond C in the 1600 range, and a C single bond C in, again, the fingerprint range. So again, the strength of the bond, that's an important factor in deciding where you expect that peak to be, and the other is whether it's a stretch versus a bend. But for each bond, you can have more than one peaks in your entire IR, which is why it will seem more complicated, than what it really is. But you, again, only have to focus on the pertinent peaks, the peaks that are visual, the peaks that can be seen and analyzed. So again, for an alkane, you're expecting a 2960. For an alkene, these two are the peaks that we are interested in. For an alkyne, the 2100 and the 3300 are the peaks that we are interested in. And the absence of these two will basically give you an idea whether it's an alkyl chain or an alkenyl chain or an alkynyl chain. So whether you have a triple bond present, a double bond present, or only a single bond. That can be highlighted by the absence of the 1640 and the 2100 in your IR. Likewise, if you have, like I said, if you have an OH, you do expect a strong broad peak at 3400 or so. If you have an NH, essentially, it has a very characteristic split peak It's sharper than OH, but it's broader than a CH, so be aware of that. Butanol. I'll give you some examples now to kind of start getting used to IRs if you haven't done that previously. Butanol means it's a 1-butanol, so 1, 2, 3, and 4. Okay, so when I look at this IR, what am I seeing? Of course, there's a whole boatload of, there's a whole boatload of things that are going on in this region, which is the fingerprint region, and I'm not interested in seeing all of that. But we will definitely pay attention to this part, the rest of the part. You see an OH, so you do expect a broad peak at 3300, and you do see that. Is there a free methyl? Of course, look at that side arm. There is a free methyl. And then there are 2 peaks right over here, which are for the CH2. So it looks like I have my CH2, I have my free methyl, and I have my OH. I have all the peaks that should be present in 1-butanol. So this is an IR spectrum that is, that will pass for 1-butanol. Now the C single bond O, that should be in the 1100 region, and there is a strong peak right over here. So we do have the peaks that we desire. Now I have a question. Let's say you had, instead of 1-butanol, you had 2-butanol. What do you think, based on what you have heard? What do you think? What would the spectra look like? You expect an OH, you expect free methyls, and the number of free methyls is not going to be, taller or longer. It's going to look pretty much the same. And then we have the CH2 as well, the CH and the CH2s that are clumped together right in this range. So do you expect the isomer of 1-butanol to show up at a different spot? And the answer to that should be no. Since IR basically is giving you information on the functionality, 1-butanol or 2-butanol are going to look exactly the same. Let's change the butane to maybe pentane. So let's say you have pentanol, 1, 2, 3, 4, 5. I still have the OH, I still have the CH2s, I still have the CH3. What do I expect? Should be exactly the same. So what's the downside of an IR? The downside of the IR is that the number of carbon atoms that you have in there, or which particular carbon atom is the functionality located in. That means the ability to differentiate between structural isomers may or may not be, or positional isomers more so rather than structural. That may not be possible in this case because IR is looking for a functionality, and if it finds that functionality, it gives you the peak. So you can say positional isomers may not be. Positional isomers may not be seen or differentiated in an IR. Let's switch gears. Maybe put in 1, 2, 3, 4, 5 pentanol and maybe cyclopentanol. Can you differentiate these two? Well, you do have the OH in both of them. You have the CH2s, and you have a CH3 in here. So what would be different? Hopefully you can see that since in case of cyclopentanol, you don't have a free methyl, that side arm that we have been referring to at the 2850 is going to be missing. So can IR differentiate between pentanol and cyclopentanol? Totally, yes, it can. So realize that sometimes, depending on the structure, you would be able to use IR to differentiate. At another time, you may not be able to. So if you're asked, if you're given two such compounds, and you're asked whether or not you would be able to use IR to differentiate those, it's a good idea to kind of draw the structure before you make that call. And so for instance, let's try 1, 2, 3, 4, 5. So I have one pentene, I have two pentene, and I have cyclopentane. All of them have the formula C5H10. And the question is, well, which ones can be seen on IR? Hopefully you can, or which ones can be, distinguished on an IR rather than seeing. Let's use the word distinguished. How would you go about it? You would say, well, in this case, you have a double bond. You have a double bond here too. So both of these are going to show you the 1600. Would the cyclopentane show you the 1600? No. So no 1600 in case of cyclopentane. Let's call it A, B, and C. So 1600 is present here. 1600 is present here. No 1600 present in the cyclopentane. You have the free methyl. In two of these, you have no free methyl. So the 2850 sidearm, 2850, the 2850 sidearm, but no sidearm over here. The CH2s are going to show up. They're going to overlap all together at 2900. That's going to happen here as well, 2900. And you will see that here as well, 2900. The C double bond C, that's going to show up as 1600. We already talked about that. The hydrogens, those are vinylic. So there will be a peak at 3000 or 3050. Well, you have vinylic peaks here. So there will be a 3050 here as well. There is no 3050 there. So if somebody asks you, well, how are you going to be able to differentiate between the two? The answer to that is, well, you cannot actually differentiate between A and B. Those isomers cannot be. But you are able to differentiate between A and C. So even though those are isomeric, because there is a difference in the functionality, you would be able to differentiate between the two. But A and B, those are again positional isomers. It's just the location of where the double bond is. Since the number of carbon atoms, the rest of the functionalities, the rest of the groups are exactly the same, you can't see the difference between the two on an IR. Can you use mass spec for that? The answer to that is no, because the molecular ion is the same. You do have free methyls in both of those. Loss of each free methyl is going to be recorded exactly the same way. So what can you use to distinguish between the two? NMR is the answer, and we'll discuss that separately. Just very quickly, I'm going to browse through a couple more IRs. Butylamine, so again, 1, 2, 3, 4, NH2. The NH2 is what is showing up as a split peak. Notice the free methyl for the free methyl in the structure. And this part is the CH2. And so again, the location, the presence of the peaks and the groups matches the structure. So we have make predictions. So again, a reminder, if you have an aromatic compound like benzene, for instance, you do see the C double bond C, so that's the one that's showing at the 1600 or the 1600. The weak 1600 to 2000, those are usually the overtones which are associated with substituted aromatic rings. So they won't show in benzene, but they will show in something like toluene, for instance. The CH is going to show up at the 3030. And so the presence of these peaks is going to give you the evidence that an aromatic compound is present. Okay. Depending on whether it's an aldehyde or a ketone, and whether the system is saturated or whether there is resonance associated with that compound, the peaks are going to be somewhere around 1690-ish or so, all the way to 16 or 1730. And then realize that a carbonyl could also be present in a carboxyl. So if it's a carboxylic acid or an ester, that tends to go a little bit higher, around 1750-ish or so. But right now I want you to think about why is it that when you have benzaldehyde or cinnamaldehyde, you have like a alpha beta unsaturated type of a system, and that's showing up at 1705. On the other hand, if you have a saturated aldehyde, that's showing at 1730. Why is that? And if you're thinking resonance, you're right. Essentially, oxygen is going to pull electrons towards itself, and these electrons are going to have to move. That means at any given point of time, the carbonyl doesn't quite have a completely double bond like character, but also a single bond associated with it, a single bond character associated with it, because of that partial delocalization. And that is the reason, since you don't have that many electrons, you don't require that kind of energy to show the electronic movement, and so the wave number is going to be slightly lesser as compared to a saturated aldehyde, in which case you're going to see a true double bond, and so you're going to see a higher amount of wave number associated with that particular structure. It's the same story with ketones also. Traditionally, a ketone such as acetone would show up at 1715. On the other hand, when it's unsaturated ketone, that tends to show up a little bit lower, and the reason for that again goes back to the fact that there's partial delocalization, so electrons move, and the C double bond O is not really a C double bond O, but rather has a slightly single bond character, and so since it doesn't have that many electrons, in order to move the electronic environment, that in order to set up that dipole, you don't require as much energy, and so it will be slightly lesser as far as the wave number goes. Okay, so this is 3-hexanone. That would mean that the third position has a ketone. 1, 2, 3, 4, 5, and 6. And now if you had to assign which peak corresponds to what, you would say, well, you see the free methyl peaks. So that's right over here. That's the methyl. This segment here is going to be the CH2s. The C double bond O is going to be right over here. And that'll be it. That will be your 3-hexanone. Again, if you're comparing that to 3-pentanone, essentially the IR is going to look very, very similar. So you won't be able to distinguish between 3-pentanone and 3-hexanone because the functionality is exactly the same. Likewise, you won't be able to distinguish between 3-hexanone and 2-hexanone because the functionality is exactly the same. On the other hand, if you had 3-hexanone and hexenal, one, two, three, 4, 5, and 6. So if you think about hexenal, you would be able to distinguish between them. Why? The C double bond O is going to be at a slightly higher wave number for the case of the aldehyde. The CH, that's the more important one. The CH of the aldehyde, that shows up at around 2700 or so. So if you see peaks in the 2700 right before the free methyl, you can say that an aldehyde is present. All right, the theme for resonance follows aldehydes. You see the same thing in case of esters as well. So saturated ester, for instance, is at 1735. The alpha beta unsaturated system is at 1715. So in addition to the C double bond O, you would also see a C single bond O in this case. That will help you assign a structure for that particular spectra. When you're looking at a carboxylic acid, you have a C double bond O, which shows up at 1700, but then you also have the OH, which in case of a carboxylic acid shows up around 2500 to 3300, in that range. And if you actually compare the same structure, so let's compare apples to apples. Let's say you have a 3-carbon carboxylic acid, and you're comparing that to, let's make a isomer of this. So you have a 1, 2, 3 carbon carboxylic acid, propanoic acid, and you have 1, 2, and a 3. You have the 2 oxygens. Yeah, everything else is the same. Notice the functionality is completely different in both of these two compounds, so you do expect them to be different. But if you look at it with the face value, you would say, well, I see a C double bond O, I see an OH, so they technically should show a very, very similar IR. But realize that the location of the bonds that you have in this particular compound is going to play a very important role. So, for instance, you can perhaps see over here that as the oxygen pulls the electrons towards itself, the lone pair of electrons from this oxygen is going to be contributed into that bond. So, in other words, you can see that this section has resonance again. Over here you have a free carbonyl and you have a free alcohol. What does that mean? That means that there is no real link between the carbonyl and the OH. And so in that sense, you can say that the carbonyl is going to show up at 1715-ish or so, and the alcohol is going to show up at 3300 as a broad peak. You're going to see the OH in case of carboxylic acid to be pretty broad too. But because there is an electron withdrawing group which is right next door, which is the C double bond O, since it's going to pull electrons towards itself, that is going to actually show up at 2500, so much earlier as compared to the 3300 in case of a true alcohol. So alcohols show up the OH, a broad OH past the 3300 mark. On the other hand, carboxylic acid, because they are right next to the C double bond O, they actually show up much earlier as compared to the alcohols. Let's take a look at pentanoic acid. So pentanoic means we have total 5 carbons. 1, 2, 3, 4, and 5. You do expect a C double bond O right over here. You expect an early OH, so 20, 24, 2500 onwards, keeps going up until 3300, so pretty broad right over here. All the CH2s, notice they have kind of they have an overlap with the broad OH that you're seeing, but they're there, and the free methyl as well. So all of those do point towards a pentanoic acid, but the giveaway is the presence of the C double bond O and the really broad OH that you see. If this was an alcohol, this would have shown up. Let me erase parts of this so you can see a little bit better. If this was an alcohol, let's also do it in blue, it would look like this. That means you would be able to clearly see the free methyl, the CH2, and then that will go as the OH. But this is a carboxylic acid, So it doesn't show up like that, and it rather actually starts going down around 2400 and shows that broad peak up to about 3300. Okay, let's see if we can apply everything that we heard in the last hour. The question is, identify the functional groups and compounds that are responsible for the following absorption. So this is a pretty straightforward question. It's only asking you what absorbs at 1710. And if that is the only peak, you would just basically say that it's a C double bond O, because they haven't given you much information about the CH. So let's not claim whether it's a ketone or an aldehyde or a part of the carboxylic acid. Let's just say it belongs to the C double bond O. A compound with a strong absorption at 1540. That's pretty characteristic for a nitro. Now you might be wondering, how do I know this? You can use the table. The table will be provided to you in a test. So use the table. But the more you practice, the better you get. A compound with a strong absorption at 1720 and a 2500. So that's very definitely a carboxylic acid, which will show you this kind of an absorption. How might you use IR spectroscopy to distinguish between the following pairs of isomers? So you have an alcohol, you have an ether. Hopefully you can see that there will be a broad peak. For the OH, there will be a free methyl group at the 2850, 3300, and there will be a 2900 for the CH2. In case of the ether, you're not going to see the 3300, so absence of the 3300 in the dimethyl ether spectra will be indicative will distinctly differentiate between the two. You will see the C single bond O in this case, however, at around 1050. And there'll be a free methyl for that at 2850. Cyclohexane and 1-hexene, we discussed that actually earlier. I gave you the example of cyclopentane and 1-pentene and 2-pentene, so you can work on that yourself. The other part of this question basically deals with your given structures, and you have to predict where the peaks are going to show up. So you should use the table to practice, but this is what you should get. You should see a free methyl at 2850. You should see the CH2s at 2900. You should see the C double bond O, and since there is resonance, it better be less than the 1725-ish or so. So I would say around 1710. This is an aromatic ring, and the C double bond Cs are going to show up at 1600. It is mono-substituted, so there will be overtones between 1600 to 2000. The CHs are going to show up at 3050s, and that will show you exactly what you expect in an IR. Let's take a look at the second one. You have a free OH, so that should show up at 3300. You have a free methyl, that should show up at 2850. The CH2s, all of these, are going to show up at 2900. The C single bond O should be at 1050. If you think about the NCH3, the free methyl, of course, the NH at 3300, that's your split peak. That's less broad as compared to the alcohol. Free methyl at 2850 and CH2s at 2900. And the presence of those peaks is going to show you the presence of the compound. Okay, I think that'll be all for IR, and you can refer to the NMR through the screencast.